Welcome to this continuation of the Nottingham celebrations of 100 years of Einstein's Years of General Relativity. My name is Jorma Kouluko. I am an associate professor in the School of Mathematical Sciences here. And it is my great pleasure to welcome today's speaker, Professor Ed Copeland from the School of Physics and Astronomy. So the format is that we'll have a talk of approximately 40 minutes, and then there will be a question and answer period. Most regrettably, there will not be refreshments after the question and answer period. This is a public lecture. We welcome questions at all levels of expertise. And if Ed spots an appropriate expert in the audience, feel free to redirect the question.
I will.
So questions at all levels are welcome, but as this is a public lecture, we particularly welcome questions whose answers do not require detailed study, detailed previous knowledge of Einstein's theory at the technical level. You cannot ask a question that would be too elementary for the purposes of this talk. So let me say...
That's an ambiguous statement. That's an ambiguous statement.
So let me say a few words about tonight's speaker. So Ed started his university studies at University College London, and then became PhD at the University of Newcastle. He did postdoctoral research at Imperial College London and at Fermi Lab near Chicago in the US. Then he became an academic staff member at the University of Sussex, was there for more than 15 years, I believe, rising through the ranks, became a full professor. And then about 10 years ago, he moved to Nottingham for a chair in the School of Physics and Astronomy to start up a particle theory group, and it continues to lead the particle theory group there, and has overseen the growth of the group into one of the major cosmology particle astrophysics group in UK. At last count, I think the web page shows approximately 30 group members, close to the figure, including seven members of academic staff. So Ed's research has been recognized by a number of merits and so on, has gained support from a variety of research councils. Let me just mention that recently he was awarded the Wolfson Merit Award from the Royal Society, and 2 years ago he won the Institute of Physics Rowling Medal and Prize for his contributions to theoretical physics. In addition to creating science, Ed has a passion for communicating science to the general public. Ed is a frequent speaker at outreach events, including outreach events at local schools, and he has contributed to two web video series about science, the Nottingham 60 Symbol series and a number file series about which I only learned yesterday when I pointed in that direction. So today the topic is the state of the universe. Would you please join me in welcoming Ed Copeland?
Thank you. Good evening. So I assure you there's no question that's daft enough. Just ask anything you want, because I probably won't know the answer. King's College London, not University College London. They're enemies, right? I mean, crikey. I'll lose my membership card if I... Yoma's in the maths department and he hasn't heard of Numberphile, and Numberphile's got 1.5 million subscribers to it, so we have to introduce you to Numberphile. That's your universe. About 400,000 years after the Big Bang, if the Big Bang is the way we describe its evolution. And it's all of your observable universe. And if I put it in perspective, the universe we think is about 13.8 billion years. So this is the picture. If you or your children live to be 100 years old, this is the picture of them after a day. Okay, just to give you a figure, this is the universe after a day if it was going to live for 100 years old. And the thing that I want you to look at there and notice is it's got these spots on it, right? And these spots are representing temperatures, but they're incredibly small temperatures. There's a symbol there, mu K. Mu means a millionth. K is a Kelvin. So water freezes at about 273 Kelvin. So you'd call that cold. These temperatures are plus or minus 300 millionth of a Kelvin. So they're very small fluctuations. It actually means that overall the universe is very smooth. It's very homogeneous and isotropic. It looks the same in all directions. And what you're looking at here is having subtracted out the uniform temperature, which actually, as we will see, is at a temperature of about 2.7 Kelvin. What you're left with are these small fluctuations. So why am I harping on about this little picture? We believe that those fluctuations are actually a remnant of the physics of the very earliest moments of the universe. The physics that went on about 10 to the minus 34 seconds after the universe began. That's 0.0000000, is it 34 zeros and a 1 seconds after the universe began. That it left an imprint, and that imprint is what you're seeing. And one of the goals of the people here, hey, it's my daughter. One of the goals of what we work on here is to try and understand the origin, is to try and understand the nature of the physics that went on that led to this early picture of our universe. And we'll come back to that a bit later. There are very few equations. There's one equation in this talk tonight. So the goal simply is you just need to have a healthy imagination. That's all I want. And what I'm going to try and do is show how, given that this is the centenary of Einstein's theory of general relativity, or his general theory of relativity, to show you how that can be used to help explain what we believe is the evolution of our universe from the very earliest moments to today, some 13.8 billion years later. And perhaps the punchline is, when the clouds have gone, they're everywhere right now, but when they've gone and you look up in the sky, and maybe you're not in London, maybe you're out in some wonderful place where you can see the night sky, and you see the Milky Way, and you might be able to see the Andromeda, the thought that when you're looking at these distant galaxies, the distribution of those distant galaxies is a thumbprint of the various earliest moments of the universe. Okay? It's not just some random distribution, it's actually telling us something about the physics that went on in times, energy scales that we'll have no way of ever approaching through laboratory experiments. So it's one of the beauties of doing cosmology, that you can in principle test these incredibly extreme conditions. Let's just try and place ourselves in context. This is perhaps one of the most iconic images taken. It's the Earth. It's taken from one of the NASA missions to Mars, the Apollo missions to Mars. And the Earth, it's this beautiful blue planet. It's about, just to try and give you scales, it's about a scale of about 12,000 kilometers across. And we orbit a sun, which is a very volatile object, fortunately, because it's the radiation from the sun that keeps us alive. And the sun's a huge thing, right? It's about 1.5 million kilometers across. Its distance from us is about 150 million kilometers. And when you begin to reach such massive distance scales, you introduce a new unit. Okay, so in astronomy you use the unit of astronomical units, and that's the average distance between the Earth and the Sun. But the Sun is part of a solar system. It's the key part of a solar system, and we are formed of many planets. We are one of many planets orbiting around the Sun. And of course, Pluto was relegated to a not major planet. And but then, just earlier this year, was this fantastic mission that went past Pluto and took these incredible pictures of Pluto, demonstrating that it looks like it's got ice sheets on it. It may even have water on it. And so there it is. I refuse to let Pluto go. It's part of my solar system. It's my slide, it's my talk, it can be my solar system. And the sort of scales we're now talking about for our solar system, we're moving out to about 5 billion kilometers, okay? About 40 astronomical units before you begin to just leave that region. But our solar system is just one. Oh yeah, this is a neat picture. If you ever want to feel your role, your position in the universe, are we significant or not? This is taken by the Cassini spacecraft that went past Saturn in 2006. It's not the beautiful rings I want you to look at right now. I want you to look at a little dot. Can you see at the sort of about 4 feet down on the outer ring, there's a little white dot? Can you see that? That's the Earth. That's the Earth as seen from the Cassini satellite passing by Saturn. It's not shining bright, it's not saying, hey, look at me, but it's there. We're just one of many planets out there. Of course, our Sun is a star. It's a star that lives within a galaxy. Our own galaxy is the Milky Way. And if you look, as I said, if you're lucky enough to be in a dark place in the universe and on Earth, and you can look out in the sky and you will see an image like that, just a band of stars going across the sky. I've only ever seen this once when I was in India, and you just have to stay there and just stay for about 10 minutes, and it just kind of lights up as you can begin to see more and more stars. And I'm sure those of you who have been to these amazing places, and you just look up and suddenly it's there. It is a band going across the center of our Milky Way. And we live we're part of our galaxy is called a spiral galaxy. And so this is an image of the Whirlpool galaxy, just so that you can get an idea of the spiral arms. We live towards the edge of one of the spiral arms. And so the typical diameter now that we're talking about, we have to move to an even bigger length scale. We have to talk about light years, the distance light travels in a year. So the typical diameter of our galaxy is about 100,000 light years. 1 light year is about 10 trillion kilometers. We're getting to big, big scales, right? But this is still small compared to the universe. And this galaxy of ours contains, about 200 billion stars, we think. No one's counted them. And that'll be a big project. And one really weird and wonderful thing that seems to be occurring with galaxies is that in the core of each galaxy, in the center of each galaxy, is a supermassive black hole. And by supermassive, I mean a black hole that's the mass of about a million stars, up to 1 billion stars. And one of the big unknowns in astrophysics is how on earth did these supermassive black holes form? Because they seem to be integral to our understanding of the dynamics of galaxies, but we don't seem to understand it. And these black holes are where Einstein's general relativity come into their own, because they've got these strong gravitational fields. So this galaxy that we live in, which is 200 billion stars, is one of approximately 200 billion or so in the observable universe, we think. And this is a phenomenal picture that was taken by the Hubble Space Telescope, and it's probably the deepest image that we've ever had in the optical light of our universe. So there are objects in this picture, the faint blue objects, which are around 11 billion light years away. That means the light from those objects left them and arrived in the in the lens of the Hubble Space Telescope 11 billion years ago, which is really remarkable, right? That you're looking, when you look out in the universe, you're not just looking at distance scales, you're looking back in time. It's one of the phenomenal features of cosmology, that you can say something about the evolution of objects by looking back out into the universe. So those objects are some 10 to the 22 kilometers away. And in fact, our universe isn't static. One of the features that Einstein refused to accept when he came up with the theory of relativity was that the universe was expanding. There was evidence around 1915 by an astronomer called Slipher that was looking at distant nebulae, and he was realizing these distant nebulae seemed to be moving away from each other. He was looking at the light from this distant nebula and discovering that the light was getting redshifted. And the interpretation of that was that the universe itself was expanding. So you could think of the space-time of the universe as being some sort of sheet on which these nebulae were living, and the sheet was stretching apart, was stretching. And that motion of the stretching manifests itself in the separation of the distant nebulae. Einstein refused to accept this. He thought that the universe was static. As far as he was concerned, when you look up at the night sky, it just looked the same, day after day after day. There was no other real evidence. But then he discovered, as did other people, that his equations, his general relativistic equations, when you applied them to the universe, just refused to let the universe be static. It kept evolving. This space-time kept either expanding or contracting. So he introduced a term known as the cosmological constant term, which he was allowed to. It was perfectly consistent with his underlying symmetries that he needed for the theory. And this he used in order simply to stabilize everything, to make the universe static again. And it wasn't, he did that about 1917. And it wasn't until 1930 when Eddington demonstrated explicitly that those equations themselves were unstable and led to a universe. If you just perturb this nice static solution, it began to expand again. That Einstein eventually accepted it. And one thing that's neat, there's a blackboard here at Nottingham. He came and gave a lecture in 1930, June 1930. And in that lecture, which was in German, there's no record of it anymore. But I like to think he came here thinking the universe was static, even though there was evidence, not just from Slipher, but from Hubble as well, that was looking at distant galaxies, that the universe was evolving. And after the lecture, he went back to Cambridge to talk to Eddington, and there Eddington convinced him that the universe was, in fact, expanding. So he came to Nottingham in one frame of mind, and then a few weeks later he was convinced the universe itself was expanding. Not only is the universe expanding, one of the most recent and most exciting things that has been uncovered about the universe is when you look at these distant galaxies moving apart, they could move apart in two ways. They can be moving apart, but as they're doing so, slowing down, as if you're putting your foot on the pedal of a car and slowing the car down. Or they could be moving apart and accelerating, moving apart ever faster and faster and faster. And until the early 90s, we assumed that the galaxies were moving apart but slowing down. And it was obvious why they were slowing down: gravity. Gravity sucks. Right, so gravity will always try and pull things back together. So the idea was that the universe was, okay, it was expanding from the Big Bang, but it was slowing down. The universe was slowing down, and the galaxies were slowing down. Then observations of distant supernovae. These are exploding stars that for a very short period become as bright as the galaxy in which they live. Remember, a galaxy is 200 billion stars typically. A single star blows up, and for a few days becomes as bright as the total galaxy luminosity. Observations of these particular type 1a supernovae seem to indicate that the universe was actually accelerating, going faster and faster. Well, gravity sucks. Gravity slows you down. So the interpretation is there's something else which is counteracting gravity and actually dominating over it in order to cause the universe to accelerate. Well, we don't know what this is. Many of us here at Nottingham work flat out trying to understand this thing, but we don't know what it is, so we call it dark energy. So for those of you that have ever heard of dark energy, it's the stuff that's driving the acceleration of the universe. And it's weird, right? It means there's some fuel being pumped into the universe to cause the galaxies to move apart ever quicker. And the goal is on to try and understand it. And the irony is that the best fit model that does this is that same cosmological constant that Einstein introduced to try and stabilize everything. It turns out if you use it in a slightly different context, it actually causes everything to go accelerate even faster and faster. So this is what our universe is doing. It's also full of radiation. The hot Big Bang was very hot. It was too hot for particles and atoms to form stable objects. So it was full of the constituent particles in the universe, the quarks, and then radiation flying around. And then if you have radiation in a box and that box expands, that radiation cools down. Just imagine a box. I said you need a healthy imagination. Come on, get your imagination, get your box, put some radiation in, and then double the size of the box. And ask yourself, what happens to the temperature of that radiation? It now has to fill an even bigger region of the box. So the radiation itself begins to cool down. And we can predict the rate at which that radiation cools down in Einstein's theories of relativity. And you can predict that it should be of order today 10 Kelvin. In fact, Gamow in 1940s, without any observations, predicted that it should be 10 Kelvin, and then more refined calculations place it at about 3 Kelvin. Remember, 273 Kelvin is the freezing point of water. So this is really cold. And then in 1992, the Kobe satellites went up and measured this radiation and discovered that it was this beautiful black body radiation, which a black body is something that emits as efficiently as it absorbs. And it had a temperature of 2.728 Kelvin, and it was the same in all directions. Anything that's the same in all directions is called isotropic. It means that if you measure the temperature of the radiation coming at you from that side, and from that side, and it's the same everywhere from all different directions, it's at the same. That's an isotropic distribution, and that is one of the underlying assumptions that goes into the Big Bang theory. It's called the cosmological principle, that on very large scales the universe is homogeneous. That means we're in no unique place in the universe, we're representative of the universe as a whole, and it's isotropic, meaning it's the same in all directions. And this was evidence of the isotropy of the universe, and it won John Mather the Nobel Prize in 2006. This is just a summary, a timeline of where we think the universe is, okay? Just to give you an idea, at the beginning here is a kind of a glowing region, which we can call the Big Bang. We don't really know what banged. Right? We do not understand the beginning of the universe. Anyone that tells you they understand the beginning of the universe, say, nope, don't think that's quite right, or who told you? So the beginning of the universe we don't really understand, but we think we understand the physics from if you put in some initial conditions, and then which is the expansion of the universe from the bang, then we think we can explain a great deal. And so the universe underwent an early period of what is known as inflation, where it grew extremely rapidly, and then it slowed down, and then 380,000 years ago, that's that image I showed you at the beginning of the slide, that was when the cosmic microwave background radiation decoupled from the atoms began to form. And then we went through a period when the first stars begin to form, and then galaxies begin to form, and then we come further along and we enter a regime where the universe is now accelerating some 13 billion years later. And we need to understand that, right? We need to try and understand all of this global picture of the universe and try and link what's going on. What I'm trying to argue today is that what you see today, 13.7 billion years later, is a reflection of what went on in those very earliest moments, that inflationary era. It's a remarkable connection if it works. So, what about you and I? Where are we in all of this? What are we made of? Well, we're made of particles, right? And the particles are held together by forces. And it all comes under this really simple picture of the standard model of particles. And in fact, the standard model of particles is made up of 3 families. I've done them in green, blue, and red there. The real stuff that you and I are made of just come basically in this one family here, the green family. Right? That we're made up of protons and neutrons and the electrons that make up the atoms. And the protons and neutrons are made up of up and down quarks. And many of you will have heard of the electron. So an electron is a lepton, and along with the electron comes a wonderful weird particle called a neutrino. So you have the electron neutrino, which was thought to be a massless particle, but fairly recently it was realized it must have a mass. And in fact, this year's Nobel Prize for Physics went to two groups who demonstrated effectively that neutrinos had a mass. So the quarks make up the constituents of the nuclei. They undergo what is known as a strong interaction, which bind the nuclei together, that you and I are made of. The electrons are leptons, and the only difference between those and the quarks is that the leptons don't undergo the strong interactions. They undergo the weak interactions and the electromagnetic interactions. The neutrinos don't have a charge, so they don't experience the electromagnetic interaction. They experience the weak interaction, and everything experiences gravity. These other two sets of families are there. They're needed to make this model consistent, but we don't really know why they're there. Mathematically, we understand it. The muon is an absolute crucial particle in the world of large high energy physics. The reason why the particle detectors at CERN and the ATLAS and CMS detectors are so huge is simply because of the muon, so that they can capture the muon. Without that muon there, the detectors could be much smaller. So the muon is crucial to our understanding of the world of particle physics. These extra families are crucial, but we don't know why there are three families. We don't know why these particles have the masses they have. We don't know why the neutrinos have the masses they have. We don't even know what the masses of the neutrinos are. There's a lot of young people here in the audience. There's a lot of things we don't know. Okay? This standard model is beautiful. It's beautifully simple. It works wonderfully. But there's so much about it we don't actually know. We know it empirically. We can measure things, but we don't know from some fundamental theory why these properties are what they are. So you have the particles, and then you have the forces between the particles. You're used to a few of these, electromagnetism, right? Why you don't fall through your seat is because of electromagnetism. At the quantum level, the electromagnetic force is propagated by what's known as a photon. Then you've got the strong force that binds the nucleus of an atom together. So, heavy nuclei are made up of many protons, right? You all know protons have positive charges. Well, some of you know protons. Let me now tell you. Protons have a positive charge. What happens if I put two objects with the same charge close to one another? Like magnets. If I put two north poles of a magnet together, they push apart, don't they? So why don't you blow up? Okay, I'll let you think about that for a minute. And that's the strong force in action that stops you blowing up. The vector bosons tell you why the sun burns. It tells you why neutrons can decay into protons, and basically that's why we can live, because it can release radiation that warms the Earth. The graviton is the particle that at the quantum level would account for the force of gravity, but we've never seen a graviton. We don't even know how to properly encompass it in our equations at the quantum level. And that's a talk next week that Tony will be discussing, how you reconcile quantum mechanics and general relativity. And then finally comes the Higgs particle, this wonderful elusive particle that was needed to make up the standard model because it provides the mechanism with which particles acquire a mass. And it hadn't been discovered, it was postulated in the early 1960s and was eventually discovered around 2012. So a long wait for the Higgs, but it eventually showed up, and it got Peter Higgs and Englert the Nobel Prize a couple of years ago. So I thought you might like to hear Albert Einstein speak. I don't know if any of you have ever heard him speak. So I have to take this off. This is the key equation that you need when you're trying to understand the interaction of particles in a Large Hadron Collider, for example, is basically the one equation that's there, probably the most famous equation there is, right? E equals mc squared. It's telling you the energy associated with particles is related to the underlying mass of those particles. And so you can collide particles of given masses together and create energy that can then be redistributed in the production of new particles. That's how particle accelerators work. Particle come in, bang, creates a lot of energy and heat and sound, and then that energy gets redistributed into producing new particles. And hopefully if there's enough energy there, you can occasionally produce a very massive particle like the Higgs. Okay, and that's the goal. And here's Einstein himself explaining the origin of his famous equation. So let me try it.
It follows from the special theory of relativity that mass and energy are both different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal to mc squared, in which energy is first equal to mass multiplied with the square of the velocity of light, shows that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Copeland and Dalton in 1932 experiment.
So once again, when he came here in 1930, there was still no experimental evidence of E equals mc squared. And yet, I don't think anyone doubted it. It's okay, so let me begin to move through. So we have these fundamental particles. You and I are made up of quarks and leptons, and they combine to form the nuclei. So when did the first nuclei in the universe form? They formed, it's a process called nucleosynthesis. They formed within about the first 3 minutes. And the easiest nuclei to form is hydrogen, because hydrogen is just a proton, okay? And so that dominates the mass of the part of the matter in the universe that you and I are made of is dominated by hydrogen. It makes up about 75% of the mass. The next simplest to form is helium. And that makes up effectively the rest. And then the next set of elements that make up the periodic table form a very small percentage of the overall mass. The majority is in hydrogen and helium, and in fact, if you work it out, you can the chances of you sipping some hydrogen from the early universe is actually rather high. So every time you drink a glass of water, if you think it's tasting off, well, it's bloody old, and you shouldn't be too surprised. But the stuff that you and I are made of, the protons and the neutrons and the electrons, we form an incredibly small fraction of the overall energy distribution content of the universe. We make up just about 5%, okay, of the 100% that is out there. Am I making you feel insignificant yet? What about the heavier elements then? The carbon, the oxygen, you know, the rings, the gold rings that some of you will have. Well, they have to form in stars. That's the only place that they can form. And of course, the only place where you can get to them is that those stars need to explode. You know, you can't get into a star and extract this out. It has to come out, and it comes out through an explosion. So in every sense, when your parents told you you're really stardust, you really are stardust. You're made up of stuff that was created during star formation and had to be released by the explosion of stars. So basically, thanks to general relativity, we have this idea of the Big Bang, which is telling me about the global features of the universe. Not the small-scale features, the global features. So let me just sort of put it in context for you. So on large scales, the largest scales that we perceive, 13 or so billion light years, the universe is homogeneous and isotropic. Given some initial conditions which have the universe, because we don't know what banged, we don't know how the universe began. If you have some initial conditions, then the universe can be expanding. The velocities of the recession of those galaxies actually is proportional to their separation. If you double the separation, you effectively double the speed with which these galaxies are moving apart. The lightest nuclei form within the first few minutes. The universe is bathed in this radiation with a temperature today of order 3 Kelvin. It's old, about 13.8 billion years. It's, you know, going across it's about 93 billion light years across. And I put this extra bit in because it's true, but it's also topical. The universe is bathed in gravitational waves. When things orbit one another, and they emit gravitational waves, ripples in the space-time. And we're searching for those ripples. They're incredibly difficult to detect. They're very weak amplitude objects. But the effort's out there because they will tell us about the early universe and about general relativity. And today, LISA Pathfinder, you might even see it on the news tonight, you heard it here first, was launched. It actually is basically got a series of sensors on. They're testing the sensors. The hope is that there'll be a bigger mission called LISA in a few years' time, but LISA Pathfinder has been launched today as a way of testing to see whether or not the technology works. Now the universe, I've said, is isotropic and homogeneous. An isotropic and homogeneous universe is rubbish, actually. So all that build-up, you can't exist in a perfectly isotropic and homogeneous universe. Have a think about it. It's isotropic, right? It's homogeneous. That means it's exactly the same here, and here, as here, and above and down. How can things collapse? How can objects form like you, like me, like stars, like galaxies, when everything is homogeneous and isotropic? You actually have to perturb it. You have to have regions of the universe which are slightly more massive than other regions. Some regions slightly less dense than other regions. So you actually need some source of perturbations, fluctuations, in order for gravity then to take hold. Because you learn at school that the force of attraction depends upon the masses of the objects and their separation. If you can have slightly excess mass here compared to somewhere else, it will pull objects towards it. And you can begin to build up structures. And so I need a source of those perturbations. And if I can provide a source of those initial fluctuations, then we've got a way of developing structures. And that's what we will come to in a moment, what the cause of those ripples. I'll come to an image that looks a bit like that one. Let's talk about the discovery of these fluctuations. This again is the pictures of the cosmic microwave background radiation. It was discovered in 1965 when Penzias and Wilson were working with radio telescopes and got this hiss, constant hiss, no matter where they turned the telescope. And they thought it was an error. But it turned out that what they were listening to was the relic radiation from the hot Big Bang. From that moment, 380,000 years after the Big Bang, when the first atoms began to form, releasing the radiation that was present to just propagate to us today. And so it measured a uniform temperature on the sky. Then I mentioned in 1992, the Kobe satellite first began to see fluctuations in this temperature, which is 2.7 Kelvin plus or minus about 10 to the minus 5. Very small fluctuations. And these are those seed fluctuations that I talked about that you need to grow to give structures. And then in 2003, the WMAP satellite found it in ever more detail. And then in 2015, the Planck data released its map of the sky showing you these fluctuations in exquisite detail. And by looking at this, not each individual spot, but the distribution of these hot and cold spots, you can work out statistical measures of the distribution of the spots and compare them to the statistical predictions that you have from your theories as to what they should look like. And by doing that, you can rule in and rule out theories. This is an amazing plot. Each of these dots is a galaxy. And each of these dots is a Milky Way. Each of these dots has about 100, 200 billion stars in it. And what I want you to see is that there's not some random distribution of dots here. There are holes in this picture, right? I don't mean these two big white regions. I mean, you look in two of the conical regions here, and you'll see these underdense voids. And one of the things we like to understand is the nature of these underdense voids, and these are themselves related to these distribution of hot and cold spots in the cosmic microwave background. And this image is regarded as evidence that the universe is homogeneous on very large scales, because the size of these voids is not increasing as I go out. They're remaining constant. So, how can you tell how much matter there is out there? You know, you can't. We don't have a weighing scales. You can't go out and just weigh it. All that you have is light. So you have to have a combination of light and then a theoretical model that tries to explain that distribution of light. And one of the things we look for is the bending of light, which again is one of the major predictions of Einstein's theory of relativity, that the space-time curvature will bend light when a massive object is there. And that bending of light is basically proportional to the mass of the object that's there. So by looking at how light is bent, seeing the angle over which it's bent, you can infer something about the mass of that object. And then if you work under the assumption that what you're seeing is representative again, then you can infer something about the distribution of matter in the universe and how much the universe is made up of matter. And what you come is this startling conclusion is that there isn't enough matter in the universe made up of you and the stuff that you and I are made of, the baryons, isn't enough to account for all the matter that's out there doing this bending of light. It makes up 5%. There's another 25% of matter out there which isn't like you and me. So it's called dark matter. It doesn't interact electromagnetically, it doesn't seem to, it has properties that otherwise it acts like matter. It attracts gravitationally, but rather weak. It doesn't interact very much with itself. And so one of the big questions is, what is this dark matter made of? It can't be the ordinary matter, and this is where the world of particle physics comes in. There are many, many candidates for this, but no one's found it. We found evidence that dark matter is there, but no one's found it, except I know where it is. It's in Yorkshire, of course, the home of all things good, and it's in Saltaire. And so here it is. And look, it's created using the prime elements of the universe. It's a Big Bang beer. So, it's actually gone out of production, unfortunately. I tried to get some, but there you go. That's where it is, Saltaire Brewery. Indirect evidence for dark matter is seen by looking at clusters of galaxies moving through one another. This is, you know, we haven't been able to find the dark matter particles directly, but if you look at big clusters of galaxies, we know galaxies are made of radiation, X-rays, they're made of matter, they're made of this dark matter. The dark matter hardly interacts with each other, so two clusters of galaxies pass straight through one another. The dark matter hardly interacts, it goes straight through, but it's making up the bulk of the overall matter distribution. The inner region is full of the baryons that you and I are made of, and they're interacting frantically, creating radiation, X-rays, etc. And they pass through one, they stay in the middle. They heat up the middle. The two bits at the edge, they remain cold, but they have more mass. And so what people have looked for is this image here. The X-rays are seen in this image here, and then these are contour plots showing you imagine you're walking in the Lake District or something, you'd recognize these as contour plots. You'd have two mountain regions, and those are where the peaks of the dark matter distribution is. What does our universe look like? What's its geometry? A universe that is isotropic and homogeneous on large scales can have three sort of shapes. The spatial distribution of the universe can have three shapes. It can be what's known as closed, a finite universe. And that, if you go down a dimension to two spatial dimensions, looks like a ball. It could be an open universe. That's where there's not enough matter in the universe to actually close it up. And so that can look like a saddle. Or it can look like a spatially flat, infinite universe. The data suggests it's this bottom one. But it's not accurate enough to be able to rule out either of the other two, but it looks as if it's spatially flat. And the universe has to be extremely fine-tuned in order to account for the observations we see some 13 billion years into its evolution. In fact, if you measure the amount of matter in the universe after just 1 second, then it has to live between these two numbers, right? And there's a 1 at the end of that, and there's I don't know how many 9s there are here. It has to be very, very fine-tuned. The universe looks like it's omega equals 1 today, a spatially flat universe, but a second after the universe began, it would have had to look like that in order to account for the fact that it looks as it is today. And this is where the idea, so the question is, where did this structure come from that leads to all these features? And this is where inflation enters. The idea of inflation is a phenomenon that occurred in the very earliest moments, maybe 10 to the minus 34 seconds after the universe began. You have a very small initial region which is causally connected. That means light has had a chance to interact all around that region. So within that region, every part knows about every other part. And then for some reason, there's some huge input of energy into this region, and it causes it to grow exponentially quickly. over a very short period of time. And in fact, the space expands by this factor, which is, what is it, a billion times, 10 to the 27 times, in about 10 to the minus 32 seconds. That's rapid. Okay? And it ends up so that our observable universe, that red bit, after 10 to the minus 32 seconds, is about the size of a grapefruit, but it's causally connected, and it's flat. And that accounts for this fine-tuning that I was talking about. It can then explain, so here's an idea of how it can explain things look flat even though they might not be. This is in Cornwall, and if you look out the universe, it looks beautifully flat there, but I hope you all realize there's a curvature to the Earth, right? It's not actually flat, it just looks flat. This could be the Mediterranean until you look at this thing and it says fish and chips, £4.85, and you look at the guy in his trousers and his shoes, and you realize, no, that's not the Mediterranean. So where do these seeds come from? I finished with these fluctuating seeds. They come from this period of inflation. So you have some very small fluctuations in this field which is driving this period of inflation, some quantum fluctuations, and because the universe expands so rapidly and to such a large size, these quantum fluctuations also grow with the expansion of the universe. So this is what my wonderful diagram's meant to show. Some small initial fluctuations grow, maintaining their same size, and those are the peaks, these small ripples on the pond, which then can lead to structures forming, because they affect the space-time in those regions where they're growing and decreasing, and they lead to these hot and cold spots. They have a certain power associated with them that you can fit with theory, and I don't expect you to give me the skull and crossbow, to look at this in detail, but the blue line is a theoretical fit to all these data points. And it's just, the fit is remarkable. And we don't really know why it works so well. So I won't do Sir Isaac. So today, dark energy is dominating the universe. We don't know what it is. This is a big challenge for any of you that's interested. What makes up 70% of the universe? The theoretical predictions of what its value should be are way higher than what we observe it to be, and we don't really understand why that's the case. It's one of the fundamental questions that we have about our understanding of our universe. And we end up with an inventory which is basically that the universe is made up of dark energy, driving this accelerated expansion, dark matter, which is accounting for the lensing and the clustering of galaxies that we see, but we don't know what the dark matter is made of, what the particles are, and the bit that we do know, the baryons, you and I, which are making up about 5% of this overall budget. So we know that gravity, coupled with the standard model, works very well. It explains a lot of things, but there are many issues that remain to be resolved. How can they be reconciled? Quantum mechanics and general relativity. That'll be the talk next week of Tony, working on about quantum gravity. So there's still lots to do for those of you who are interested. But the key thing, as far as I'm concerned, and why I do a lot of outreach stuff, is to do all this, the key thing is to have fun. Okay? If you don't have fun, don't do it. Go and earn a lot of money doing something else. Fun has to be the goal. And this is me having fun at the particle detector.
Where?
Oh yeah.
Wow!
Thank you. Thank you.
Thank you very much. We will be happy to take questions, and I will say again, no question will be too elementary. I hope you are happy with that formulation.
I'm going to ask a very elementary question about neutrinos and their mass, or lack of it. It seems strange that we've taken such a long time to ascertain the mass, or the rest mass, I mean, of a neutrino. neutrino? Why is it taking so long?
It's worse than that, we haven't. So the question was, why is it taking so long to determine the mass or the rest mass of the neutrino? We don't actually know the individual masses. We know mass differences. The reason is they're so weakly interacting. Put your thumbs, look at your thumbnail. Okay? All of you. Come on. Look at your thumbnail. There's about roughly 100 million neutrinos going through there every second. Yeah, you might feel, occasionally now you'll feel a bit itchy. That will not be the neutrinos. So they are incredibly weakly interacting. So in order to get any evidence for them, you have to go deep underground, and so that you can maximize the chance of them hitting a nucleus and causing the nucleus to recoil, for example, and then picking up the recoil energy and the recoil momentum of the nucleus and inferring something about the neutrino from that. And that's what the people that won the Nobel Prize this year, that's what they did. There were two major observatories, one at the Snow Lab in Canada and one at the Super Kamiokande Lab in Japan. Each were filled with heavy water, so that the heavier the particle is, the bigger the cross-section for a neutrino to hit it and scatter off it. But still, they were at their best, they were finding maybe a collision a day. And then, in order to be sure that what you're seeing is a neutrino, as opposed to some, say, cosmic ray or some other radiation coming from the rocks around you, you have to build up the statistics. And if you've got an event or 10 events a day, 10, I think it was definitely not 10, then you've got to wait a long, long time in order to make sure that what you're seeing is evidence of the neutrino as opposed to the something else. And so that's part of the reason why it takes so long. The neutrinos just don't interact. They're weakly interacting particles.
The energy that caused the inflation, did you say it was dark energy?
No.
So, are there any ideas as to where that energy came from? Was it already in the universe? Is it still is?
Well, that's a good. Where did the energy for inflation come? Which is kind of linked to, in some sense, where did the energy for the universe to bang? But the energy, the models that people have for inflation are based on what are known as scalar fields. And up until 2 years ago, these were speculative objects which we didn't really know if they existed, but the Higgs field is an example. And the Higgs has now been discovered and shown to be this object called a scalar field. A scalar field is very simple to understand, so don't panic. Temperature is a scalar field, right? Temperature is what a scalar field is, something that's just got a value. It doesn't have a direction. A vector field is a thing that has got a value and a direction. So the temperature here is maybe 26 Celsius, and over here might be 28 Celsius, and here is about 150 Celsius. But I don't say it's 150 Celsius in that direction, right? So that's what a scalar field is. It's just got a value, and the thing that we believe are present in the early universe, which we would like to link to some fundamental theory, perhaps like string theory or some quantum gravity theory, is this scalar field. It has an energy, a potential energy, and it's that drives the initial period of inflation. Unfortunately, at the moment, we just have to basically speculate where it's coming from. There are models of string theory which will give me the inflation, and it links the inflation to the evolution of the extra dimensions of string theory. But we don't know if that's the correct one yet. It works very well, but we don't know if it's right or wrong. So we don't know where this underlying energy density has initially come from, but we say that it comes from a scalar field.
You made a point of this assumption that the universe is isotropic and homogeneous. So for what times are we assuming that? Like, is that for all times, or is it just at the beginning of the universe? Or is it just
So the point made was I've made the assumption that the universe was isotropic and homogeneous, and the question is, for what times is that assumption made? It's made probably pushing it too early into the universe. It's pretty much assumed from the period of inflation that inflation actually forces you into a period of effective isotropy and homogeneity. That was one of the reasons it was introduced. And so it's going from 10 to the minus 30 seconds or so. there is still some debate as to whether or not the universe really is that. The isotropy, I think, is fairly convincing. Looking at the radiation from the cosmic microwave background, the homogeneity is much more difficult. Because the homogeneity is about your neighbouring region, not looking at distant light coming to you from distant objects. It's about your region, and so you've got to be able to go and look at different regions to do this. And as you saw, the best we can do is with galaxies, really, galaxy surveys, and they're limited by how far back you can see. But the interpretation is that it works. The thing that also backs it up is that you can do numerical simulations, for example. You could have a universe in your computer which has inhomogeneity in it. And you can ask how much inhomogeneity can you allow before what you see in your simulations differs from what we see observationally. And it turns out it doesn't look like you can have too much inhomogeneity.
What is the universe expanding into?
No. What is the universe expanding into? The space-time is being created as the universe expands. So it's not a situation. The closest analog I think you can probably come across that kind of makes sense is, imagine you are living on the surface of a sheet or a balloon. Okay, you're on the surface. You cannot look out from that surface. You must not look into the center because you are on the surface, and the balloon's expanding. And that space-time is being created as the universe expands. So it's kind of the analog of that. It's not that we're expanding into something that's something bigger. The space-time is everything. Yeah, it's hard concept. How do I know that? I don't. I don't. Right? I mean, so that's a really important question, right? And how do you test these theories? I mean, what you can try and do is if it didn't, right, then there's an edge, right? There's an edge. There's a place beyond which there'd be something else out there, and we're not seeing evidence of that edge. We know the universe is incredibly big. It could even be infinite. We don't know if it's infinite. That's kind of an analog thing here. Our observable universe is increasing as time goes by. We can see further back, and we don't see any evidence of any edges appearing, which I think would be an example of it. I'm not sure. I think it would be something like that. I mean, not equivalent, but another thing people look for to do with this geometry is maybe our universe isn't quite as simple. The geometrical shapes of our universe isn't quite as simple. Maybe our universe has some holes in it. It's got some topology associated with it, like a torus, and people certainly look for evidence of that, because if there was something like a torus, imagine we lived on a torus, a donut, right, and you weren't going to eat it, then as you go around the donut, you'd come back to yourself. So people do look. They look out into the distant universe, and they look for evidence of things repeating themselves. Distributions of galaxies which look the same as I keep going back, and they haven't found any. There are some quite tight constraints, for example. So if the universe is like a donut, it's an absolutely massive donut, because we see no evidence of being able to go around and come back and see ourselves again.
I was wondering that what would be the possible implications on general relativity if we won't be able to find gravitational waves?
If we can't find gravitational waves,
Yeah. What would be the possible implications?
it'd be huge. I think it'd be huge. As far as I know, even the current LISA Pathfinder isn't likely to find gravitational waves. It's testing the instrumentation which would go on the next generation known as LISA. It's not even clear LISA will get funding to be built, as far as I'm aware. You aware of it? So it looks like LISA will get built, but it's in, I don't know, 5-10 years time. 2034, even longer. Wow. Archie will be working on it then, along with his medicine. And so, but there are detectors looking for them now. These are the amazing LIGO, advanced LIGO, are looking for gravitational waves. Their sensitivity is such that the calculations of the most likely sources of gravitational waves, powerful gravitational waves, which are coalescing neutron stars, or a neutron star and a black hole, or coalescing black holes, very massive objects which as they approach one another really distort the space-time and send ripples out. They are reaching the sensitivity where we would expect, under theories of GR and under certain assumptions about the distribution of these objects, that we should be seeing them fairly soon. So if probably over the next 10 years we don't begin to see these, I think then we'd be questioning, either we're totally misunderstanding the distribution of these objects, or, which is possible, or we've got some issues with GR. But GR works really well. That's our problem. If we don't see them, it works beautifully in explaining the observed features of our universe.
Is there anything inherently special about the fact that we're in like a very almost flat universe? Like, can curved universes exist?
They can exist, yeah, absolutely. And
Weird things happen.
the weird things. I mean, we know the universe is very large. We don't know, it may well be curved. In fact, you know, but the errors are such that in fact the current bound on this omega k, the density of you can allocate an energy with the curvature, if you like, in Einstein's equations called the Friedmann equation. You can allocate an effective energy and say, well, how does that contribute to this thing that sums up to 100%? The current bound on the curvature is that its value is 0.000 plus or minus 0.005. So at best it's of order 1,000th of the total energy, but it could be there. It could be plus or minus that, which would indicate the universe is either closed or open. But it's consistent with zero. We'd get weird effects if it was extremely closed. In fact, you know, the universe would have recollapsed already. A closed universe is one that expands, reaches a maximum size, and recollapses. Well, we're still expanding. So we clearly haven't reached that stage. I don't know of any. I mean, there are observational consequences of it being closed. They light, you know, triangles on an open and closed universe. If you draw triangles, they either, this is one way of defining whether you're open or closed. The angles in the triangle, one of the first things we learn at school, right? You sum up the angles in the triangle, it's 180 degrees. Well, in closed and open universes, they're either less than 180 or greater than 180. And that actually is effectively how one of the ways people try and determine the curvature. They look at what are known as geodesics, and they try and determine what the angles are between them.
Is space-time inherently springy and such that it wants to expand when not constrained by gravity, or must there be a force driving it? Is it passive?
So the question is space-time inherently springy? And does it want to expand, or do you need to put something in there? Now, Einstein's, before he put in the cosmological constant to stop it, the space-time expanded. It just wants to do it. If there's some matter contribution in there, it will lead to either a contraction or an expansion. I don't know if you want to interpret that as springiness, or it's just the effect of the matter contribution. It's one. So he had to work quite hard. In fact, in order to stop this happening, he had to introduce this energy term, this cosmological constant, and he had to actually have a closed universe. He had to do both of these things, and then that meant that the universe stopped expanding. But then Eddington so now the universe is static. It's just there. And Eddington just said, well, what happens if I just kick it? You know, the pencil standing up, if I just flick it, you know the pencil will fall down because it's unstable. He did that to the universe. What he actually did was he said, let me just vary the matter in the universe, just a little bit, and let's see what happens. And he showed that the universe immediately would start either expanding exponentially quickly or contracting exponentially quickly. And so that was an unstable. So it actually wants to evolve naturally. Yeah, I don't know how to interpret it in terms of the springiness, though. That's a good question.
The university porters will want us to vacate this room at some point, but we could take up to 3 more questions.
Can I ask you about lambda and g? You talked about the universe could expand or could contract depending on these various constants. And in fact, it's always surprising, why did it take so long to realise this? Because you could write the equations on the blackboard. You know, I think we could all see that one was going to expand. First of all, why did that take so long? And my second question is, we all accept that G is the value it is, and we accept the value of the electronic charge and so on. Why is this compulsion to know what lambda is? Why can't you just say it's a constant of nature, just like G is in the expansion equation of the universe?
Okay.
2 bits to it.
2 bits. So what first question was, why did it take so long to realize the universe could expand or contract, I think? Was that?
Why did they think for so long that the universe seemed to be constant? It's clear that if you write down the universe,
Sure.
you can see it's either going to expand or contract.
Yeah.
It could be instantaneously constant, you know, a very short time, and then go one way or the other. As you say, it's like a pencil. Why did that take so long?
I have no idea why Einstein, who is probably the smart guy, I did this video with Brady, and Brady stopped me talking about that. He said, "You've done too many equations." So Einstein came up with the equations in 1915. By 1916, there was already the first set of solutions, which was actually by Schwarzschild, who was interested in, who realized that you could have black holes, nothing to do with cosmology as such. Einstein realized by 1917 that his solutions, when applied to the universe, where he described it as homogeneous and isotropic, had to have them evolving, so he did what he did. And the reason he did what he did is he believed in effectively in Marx's principle, which said that on very large scales, this homogeneity and isotropy, that on very large scales, the matter distribution shouldn't be doing very much. And I think that's what drove him, because he hated the idea of a singular beginning. And all of his solutions had to have a singular beginning. There was no real way out of that. And so he did this to avoid that. And then the universe didn't look. Slipher's observations, if you go and look at Slipher's papers, it's very difficult to determine the results in terms of an expansion of the universe. He's just looking at the redshift of the light from the distant nebula. He's not interpreting it at that stage. Hubble began to interpret it. In 1928, 27, 28, Hubble began to interpret it. And by 1930, Eddington had shown the instability. The bit I really don't understand, Einstein came up with his solution in 1917. Why he didn't just ask about the stability of it, I think he did. And I think he knew it was unstable. He thought, oh.
And why don't you accept lambda system?
Oh, lambda, because...
Do something else.
Yeah, do something else. Because there are many facets in physics, many features in the world of quantum physics, which can provide an energy content that looks like a cosmological constant. And in fact, when you work out what their contributions are, they're much larger than the cosmological constant, which seems to be driving the acceleration of the universe today. And we don't really know how to deal with them. We have to subtract them somehow, because they would have totally changed the way the universe is evolving, and they don't. They're not perceived to be there, and so we have to try and understand that. Otherwise, I think if that wasn't the case, we would effectively say we would really like to know where lambda comes from, but it's a parameter.
One more question, if there is.
That's technical, isn't it? The universe is expanding, and you said it's accelerating as well. Has it always been accelerating?
No, it's really important that it hasn't always been accelerating, because the question is, has the universe always been accelerating? So we think that there was a very early period of acceleration, that's the inflation. Inflation finished, and actually there was lots of interesting physics went on as the universe reheated, but then it entered what we call a radiation and matter-dominated regimes. And in those regimes, it slowed down. And it's very important it slowed down, because if it hadn't slowed down, if it kept accelerating, then those small fluctuations which I talked about, which then allowed particles, matter, to start accreting, they wouldn't have been able to do it. The expansion would have just pulled them all apart again if it was accelerating. So we need to have a period of deceleration where the particles that can begin to attract gravitationally and lead to structures and galaxies and stars and planets and you and I. And so the observed acceleration probably began about 7-8 billion years into its evolution. It's been accelerated for quite some time, but nowhere near as rapidly.
Thank you very much again indeed.
Okay.